Namaste everyone, welcome to Vidya School YouTube channel. Myself Moses, chemistry teacher. In this video we are going to discuss alcohols, phenols and ethers in one chat. Okay, let us see what we are going to discuss in this video. Okay, we will see first classification of alcohols, okay, followed by structure of functional group and preparation of alcohols and phenols, physical and chemical properties of alcohols and phenols. Okay, these are the major points which we are going to discuss. Okay, we are not including IUPAC nomenclature here. Okay, that is a separate thing we can make the videos on. But now we are going to discuss what I can say classification, structure, preparation properties of alcohols and phenols. Right? Let us go to the next slide. Let us see the classification first. Okay, generally this can be classified into like mono, di, tri or polyhydric compound, okay, based on number of hydroxy group. Okay, generally alcohol group means what? Okay, it contains OH functional group, okay, OH functional group, hydroxy functional group. Okay, if we have one like OH group, right, that can be termed as what? Monohydric alcohol or monohydric phenol. If it has like any compound has two like hydroxy groups over there, that is known as dihydric compound. If any compounds has three hydroxy groups, right, like what we are seeing here, okay, if any compound has three hydroxy groups, okay, they will come under what? Trihydric compounds. Okay, this is based on number of hydroxy groups on the particular molecule. Okay, let us go with the type of carbon where OH bond is connected. Okay, generally what happens in the organic chemistry, like alcohols in the sense, like this OH group should be connected with the carbon, right, based on the hybridization of this carbon, based on hybridization is of this carbon. Okay, let us go with the first one. If this particular carbon is sp3 hybridized one, sp3 hybridized one, okay, simple one. Okay, like if you get confused which one is like sp3 hybridized carbon, which one is sp2 hybridized carbon, which one is sp hybridized carbon, you just remember one thing, like I am not getting into the technical details of hybridization over here, but I'll just give you a simple shortcut right now. Okay, I'll just give you a simple shortcut. Okay, if you see any carbon with 4 single bonds, right, that will be sp3 hybridized one, sp3 hybridized one. If we have any like carbon with what is one double bond over there, it will be sp2 hybridized one. If we have any like 3 triple bond between carbon and carbon over there, triple bond between carbon and carbon, this carbon is going to be what? sp hybridized carbon. Okay, I'm not getting into technical details of what is hybridization and how hybridization is going to be, but now what we are going to see here is that we are going to see what is like sp3 hybridized carbon, and when OH group is attached to sp3 hybridized carbon, generally it is classified into 3 types over there. 3 types over there. What does it mean? Now let us take the carbon, sp3 hybridized carbon, where OH group is attached. If it is connected to one alkyl group or one carbon here, okay, that will come under what? Primary alcohol. Okay, primary alcohols always will have CH2OH, CH2OH. Okay, if we take the second one here, we have 2 alkyl groups here, 2 alkyl groups over here. Okay, this might be same or different also, R dash or R dash or RR also it might be over there. Okay, based on like what I can say, like number of alkyl groups over here, if it is 2, then this particular alcohol comes under what? Secondary functional group, secondary like alcohol over there. Okay, now we have the third one over there. We'll take it as tertiary one, where we can see 3 alkyl groups of same kind or different kind, it doesn't matter. If the sp3 hybridized carbon is connected to 3 carbons over there, that particular hydrogen like hydroxy group or alcohol comes under what? Tertiary alcohol, tertiary alcohol. Okay, now let us go with the what I can say another type of classification of alcohols of sp3 hybridized carbon. Okay, if sp3 hybridized carbon is connected to sp2 hybridized carbon, for example, what I can tell you is that, let me take C double bond C, single bond C, OH. Okay, I'm not balancing the valence of the carbon over here, I'm just taking an example. Okay, these 2 carbons where carbon-carbon double bond, like these 2 carbons are connected with the double bond, right, these 2 carbons are known as vinylic carbons, vinylic carbon. Okay, next to the vinylic carbon, right, what is the hybridization of vinylic carbon? These 2 carbons are sp2 hybridized one, sp2 hybridized one. Okay, if you see this carbon next to vinylic carbon, right, this is known as allylic carbon, allylic carbon. Okay, now based on the position of OH group, right, whether it is locating at the allylic position or vinylic position, these are classified actually. Okay, now like we know this is carbon-carbon double bond carbon is there, and we have sp3 hybridized carbon next to this vinylic carbon over there. This is known as allylic carbon over there. Since OH group is connected to the allylic carbon over there, we'll call this one as allylic alcohol over there. Which allylic alcohol? This sp3 hybridized carbon is connected to only one carbon here, right? Only one carbon here. That is what it is, primary. That is what it is, primary. Okay. For example, if you take the same thing here, this is also allylic carbon because it is next to the vinylic carbon over there. Now this carbon is connected to two carbons here, one carbon and another carbon. Okay, that's what it is, secondary allylic carbon over here. Secondary allylic carbon. If you take the third one, we have the vinylic carbon. Next to the vinylic carbon, we have allylic carbon. This allylic carbon is connected to three carbons over there. That's what it is, tertiary allylic carbon. Tertiary allylic carbon. Okay, next. Okay, we have benzylic carbons also. It is also similar to allylic carbon only. Allylic carbon only. What is the difference over there, here, there and here is that here we have extra benzene ring here. Benzene ring. Okay. Now, since benzene is aromatic compound, right? The carbons which are there in the benzene is known as arylic carbons over there. Next to the arylic carbons, whatever the carbon starts, right? It doesn't matter whether it is primary, secondary or tertiary. This particular carbon is known as benzylic carbon. Benzylic carbon. Benzylic carbon. Okay. If a OH group is located at this benzylic position, right? That is known as what? Benzylic alcohol over there. Benzylic alcohol. Okay. Since this particular carbon is primary carbon over there, that's what this alcohol is, what? Primary benzylic alcohol. Okay. And the second one we have where OH group is located at the benzylic position, but two carbons are connected. Two carbons are connected. One carbon is from the benzene ring, another carbon is some other carbon is there. Like where this benzylic carbon is connected to two carbons over there, that's what it is, secondary. In the case of third one, what do we have? 1, 2, 3. We have three carbons here. 1, 2 and 3. That's what it is, tertiary benzylic alcohol. Tertiary benzylic alcohol. Next. Let us go with the preparation of alcohols. Now, we have seen the classification of alcohols and phenols, right? Alcohols we have seen especially. Now, let us go with the preparation of alcohols right now, okay? Now, the first preparation is from alkene. Our first preparation is from alkene, okay? Alkene in the sense, right, generally they will undergo addition reaction. This is also a kind of addition reaction only. What kind of addition reaction is that? It is acid catalyzed hydration. Acid catalyzed hydration, okay? For example, if you take an alkene, that is C double bond C, okay? And what is happening here is that it is acid catalyzed. Acid catalyzed means what you can indicate it with the H plus over there, right? Acid catalyzed hydration in the sense addition of water. Addition of water. What happens here? Formation of alcohols takes place. Formation of what takes place? Alcohol takes place. HOH over there, okay? Now, double bond is turning into single bond, right? This is an example for addition reaction. This addition reaction is taking place in presence of acid and addition of water is taking place, right? That's what it is, hydration of alkenes, or we can also call it as acid catalyzed hydration. Acid catalyzed hydration, okay? Now, this particular addition reaction follows Markovnikov rule, okay? Markovnikov rule, okay? What is Markovnikov rule states about? Markovnikov rule states that the negative part of the reagent goes to the carbon with less number of hydrogen, right? Now, if you take H plus and OH minus, which is added to the alkene over there, the OH group is negative part of the water over there. This negative part goes to the carbon with less number of hydrogen, okay? For example, let us take an unsymmetrical alkene, that is CH3, CH, double bond, CH2. Okay, what do we have? We have an unsymmetrical alkene, okay? Where we have two carbons connected to the double bond. One is with one hydrogen, another one is two hydrogens over there, okay? Now, what we will do? The same thing we will do, okay? Acid plus water, okay? What is happening here is that addition of H plus and OH minus takes place to the alkene over there, right? Now, where the OH minus will go according to the Markovnikov rule? According to the Markovnikov rule, it will go to the carbon with less number of hydrogen, right? Which one has the less number of hydrogen? This is the first carbon and second carbon. Second carbon has less number of hydrogens over there. That's what Markovnikov product formation takes place here. Then what is the product over there? That is going to be what? OH group comes to the carbon to the carbon with less number of hydrogens over there, okay? This is 2-propanol, okay? Follows Markovnikov rule, we have to remember. Let us see the mechanism, how it takes place, okay? Let us see the first one, okay? Let us take the first one here. What is this? Protonation of alkene to form carbocation by electrophilic attack of H3O plus over there, okay? Now, first let us take water and H plus over there. It is acid catalyzed, what I can say, hydration, right? Let us take water plus acid here. Let us take water plus acid gives hydronium ion, that is H3O plus over here, H3O plus, okay. Now let us take an alkene right now, that is C double bond C, okay. You can take any alkene, I am just taking generalized alkene over here. Now what is happening here is that let us take the protonium, like hydronium ion now, okay. Hydronium ion is positively charged on, okay. Now what happens is that now water, like the H plus acts as a electrophile and the double bond pi bond acts as a nucleophile over there. Attacking of like pi bond takes place to the proton over there. When it attacks over there, formation of new bond takes place between carbon and hydrogen. Let us take the hydrogen over there, and then adjacent carbon gets a positively charged. Okay, what is this one? This is nothing but my carbocation. Okay, in the first step, formation of carbocation is taking place right now. Okay, now let us take the same carbocation which is generated in the first step. Okay, let us take the carbocation which is generated in the next, like first step. Okay, now in the second case, nucleophilic attack of water takes place to the carbocation. Okay, now water acts as a nucleophile, that is H2O. Okay, oxygen has two lone pairs, right? Acts as nucleophile, and the carbocation becomes electrophile. Attacking of nucleophile to the carbocation takes place. What happens? Addition of nucleophile, that is water, to the what happens to the carbocation happens over there. And what happens now? The new bond will be formed between oxygen and carbon. Okay, OH plus, and what do we have? And the remaining things are same only. Okay. Now this is what is been formed, right? In the final step, what happens? Oxygen with positive charge is likely to be unstable. That's what elimination of proton takes place. That is the deprotonation step. Deprotonation step. What is that step right now? Let us take it here. The same thing. Oxygen with a positive charge, hydrogen. Okay, now what do we have? Oxygen with a positive charge is unstable. What happens? This bond pair shifting takes place towards oxygen, and elimination of proton takes place. Elimination of proton takes place, and remaining what will be there? We will get our alcohol, which we were expecting actually as a product over there, right? Now formation of product alcohol took place, right? Now this particular reaction which we are discussing as acid catalyzed hydration, right, of the alkene follows Markovnikov rule. According to the Markovnikov rule, the negative part of the reagent goes to the what I can say less number of hydrogens, that we have to remember, and we should also remember this particular mechanism. Okay, there are certain MCQs, okay, in which it is been asked something like this. What is the first step in the what I can say protonation of alkene, acid catalyzed hydration over there? Okay, they have given like protonation of alkenes, what I can say, and nucleophilic attack, deprotonation, and of the above. Okay, we should remember all the steps in order by which we can solve the MCQs. Okay, let us go to the next one. Okay, and the next one is hydroboration oxidation. Hydroboration oxidation over there. Okay, now like diborans. Okay, diboran reacts with what? Alkenes to give a trialkyl boranes as addition product. This is further oxidation to alkene by hydrogen peroxide in presence of what? Aqueous sodium hydroxide, gives alcohol, we know, right? Now let us see the reaction right now. Okay, let us take an unsymmetrical alkene. Unsymmetrical alkene, that is CH3CH, double bond CH2, double bond CH2. What is happening here is that addition of BH3 takes place. Okay, addition of BH3 takes place. BH3 takes place. Okay, it is actually a dimer. Okay, dimer is nothing but diboran. Okay, what happens now in the first step? Addition of BH3 takes place. That is CH3, CH. Okay, CH2. Okay, now what do we have? We have BH2 here and hydrogen. Okay, the number of replaceable hydrogen in BH3 is going to be 3, right? That's what 3 alkenes reacts with this one. How many alkenes reacts? 3 alkenes. Okay, now if we take the BH3 over there, we will take BH3 as BH2H. BH2H. Okay, BH2H. Okay, now in the first step we can just assume that one has double bond between carbon and carbon acts as a nucleophile, and boron having a low empty orbital, right, acts as what? Electrophile over there. Okay, and formation of new bond takes place between carbon and boron and the hydrogen also over there. Okay, in the next step, okay, what happens? Another mole of alkene takes addition of another mole of alkene takes place, that is CH3, C double bond H and CH2. Okay, what happens? another like hydrogen comes out over there and addition takes place, and the terminal carbon like addition takes place to the boron over there. Okay, then what we'll get here? What we'll get here? That is CH3, CH2, CH2B. One of the hydrogen is being added to this particular thing. That's what only one hydrogen will be there, and another mole of CH3. This one is coming, right? That is CH2, CH2, and CH3. Okay. The further, like we have another replaceable hydrogen, right? Another mole of alkene addition takes place. That is CH3, CH double bond, CH2. Okay. Let us take this one as CH3, CH double bond, CH2. Okay. And we have another like replaceable hydrogen, right? What happens here is that, let us take the boron here. Let us take the boron. How many alkyl groups are there around? Already 2 are there. Another mole will be added over there, and altogether 3 moles of alkyl groups will be there around the boron over there. That is CH3, CH2, CH2 taken 3 times. Over there. Okay. Now after this boration of alkenes, okay, hydroboration of alkenes, right? What is happening here? Oxidation is taking place. Oxidation is taking place in presence of hydrogen peroxide and aqueous sodium hydroxide. Okay, let us take H2O2 plus like NaOH. Okay, NaOH. It is in the aqueous medium. Okay, what happens here is that like formation of alcohols takes place where boron is connected, right? At that particular point, OH addition takes place over there. That is CH3, CH2, CH2, OH. Like how many moles we have? 3 moles, right? 3 moles. Followed by the formation of H3BO3 takes place. H3BO3 takes place over there. Okay. Now, if you see this particular product over here, which is formed by the what I can say like hydroboration and oxidation here. Now, this OH group is added to the carbon with more number of hydrogen, right? More number of hydrogens. Okay. If you take the initial one, and if you compare, right? Now, the first one has what I can say 2 hydrogens, and the second one has only 1 hydrogen, right? But OH group is added to the carbon with more number of carbons over there, right? It is according to what rule actually? It is according to anti-Markovnikov rule. Anti-Markovnikov rule, okay? According to Markovnikov rule, what we have discussed, actually, according to Markovnikov rule, the negative part of the reagent goes to the carbon with less number of hydrogen. But here, the negative part of the reagent went to this carbon with high number, like more number of hydrogens over there. That is why this product seems to be something like opposite to that of Markovnikov product. Okay, we have to remember in this case. Next, let us see. Okay, the second preparation method is here from carbonyl compounds. Okay, first we have discussed a preparation of alcohols from alkenes. Okay, by hydration, and second one is hydroboration and oxidation. Right. Now we will see carbonyl compounds. Okay, from carbonyl compounds, how can we prepare alcohols? Okay, so generally, if you take the carbonyl compounds, let us take a C double bond O. What I can say, kind of like bonding will be there. Okay, this one should be connected to like this one should be converted to the respective alcohol, whatever it is. Okay. Now, if we take what I can say aldehyde, it will use primary alcohol. If you take ketone, right? If you take ketone, it will give secondary alcohols R, CH, OH, and R. Okay. Simply let us take an example. Okay. Now let us take an aldehyde. We have many reducing agent, like for how this reducing agent could be used for this conversion of highly oxidized substances to alcohols. We could discuss in the lateral classes. But now let us see how aldehyde could be converted to alcohols. Now aldehyde could be converted to alcohols over there. Okay. Aldehydes in presence of hydrogen and catalyst. Okay, it might be palladium, platinum, or nickel. Okay, it gives a primary alcohol. That is CH2OH. Okay, let us take ketone. Okay, if you take ketone over there, okay, let us take R and R dash. Okay, what happens if you take ketone? It gives what? Secondary alcohol. Okay, Okay, let us take simple reagent which could be used for the conversion of ketones to the respective alcohols over here. That is, let us take sodium borohydride, NaBH4 over there. Okay, what happens here? This ketone turns into the respective secondary alcohols. Okay, this is primary alcohol, this is secondary alcohols. This is secondary alcohols. Okay. Now by reduction of carboxylic acids, by reduction of carboxylic acid. Okay. For example, if you take a carboxylic acid, COOH, right? This one converts into the primary alcohol. This one converts into on reduction primary alcohols. Okay. Now this is a kind of strong reduction. Okay. The mild reducing agent cannot be used for this particular conversion. For this, we'll use this strong reducing agent known as lithium aluminum hydride. Lithium aluminum hydride. Okay. Other reagents, this reagent cannot be used. Okay. This is a mild reducing agent. Okay. This cannot be used for the conversion of acid to the alcohol. Okay. We have to use a strong reducing agent over there. Followed by the hydrolysis, it will use what? Alcohols. Okay. Sometimes lithium aluminum hydride becomes an expensive one, right? That's what we'll do is we'll just take carboxylic acid in presence of in presence of an alcohol. We know that the reaction between carboxylic acid and alcohol gives the ester. Okay, R COO R dash over there. Okay, ester. Okay, this ester and further reduction. Okay, further reduction in presence of catalytic hydrogenation over here. In presence of catalyst, it turns the ester into the respective alcohol. That is RCH2OH. RCH2OH. Okay. Here, what we have to remember here is that this strong reagent only can be used for the preparation of alcohols from acids over there. Okay. Not the mild reagent, we can use it. Okay. For separately, we can make a video on only reagents. Okay. How can we use for reduction and oxidation also. Okay. Let us see how can we use the Grignard reagent for the preparation of alcohols right here. Okay. What does it mean by Grignard reagent? The general formula of Grignard reagent is RMgX. Since alkyl group is connected to the metal, right? Since alkyl group is connected to the metal, okay, metals are highly electropositive in nature. The one which is connected to the magnesium or metal over there becomes what? Nucleophiles are negatively charged. Negatively charged over there. Okay. Now the simple data we can remember here is that if you take formaldehyde H, C double bond O H, it gives on reaction with Grignard reagent followed by hydrolysis, it gives what? It gives a primary alcohol R CH2OH, CH2OH. And if you take aldehyde, okay, if you take aldehyde, it gives a secondary alcohol R CHOH and R. If you take ketone, okay, if you take ketone, this one gives what? Tertiary alcohol. This one gives what? Tertiary alcohols. Okay. Formaldehyde gives primary alcohols. Aldehydes gives secondary alcohols, and ketone gives what? Tertiary alcohols. So this is the basic data which we have to remember. Okay. Now let us see how the reaction takes place with the Grignard reagent and carbonyl group over there. Okay. For example, if you take C double bond O group here, okay, what happens with C double bond O group here? Let us take RMgX, okay. We know this alkyl group is negatively charged or nucleophile, right? Alkyl group acts as nucleophile and carbonyl center is known as electrophile here. Okay. Now what happens? Attacking of nucleophile takes place to the electrophile, and the generation of negative charge takes place. Okay. And what do we have? We have a R group over there, and here the positive group will come. What is the positive group over there? MgX. Okay, this is positive group over there. Okay. Now in the next step, what happens? Hydrolysis should take place, right? What happens here is that here hydrolysis takes place. To the negative part, H plus will come. To the positive part, OH minus will come. Okay, and what will be formed over there? We will get an OH group, that is alcohol, followed by magnesium, OH and X. OH, magnesium, magnesium hydroxide and halide over there. Okay. Now one thing we have to remember here. Okay. Whatever groups we may have here. Okay. For example, if we have hydrogen and hydrogen, we'll have hydrogen and hydrogen. Here also we can have hydrogen and hydrogen. Okay. Now RCH2OH is what? Primary alcohol. Okay. Now for example, if we have RCHO aldehyde over there, we can also have RO here. We'll get the secondary alcohol. Now if you take another RO here, another R will come, alkyl group will come, another alkyl group will come, by which we can get tertiary alcohols. Okay. Now which alkyl group we will take, like which carbonyl group we will take, based on that we can get the respective alcohols. Okay. If you take formaldehyde, we will get primary alcohols. If you get aldehyde, we will get the secondary alcohol. If you get take ketones, right, gives tertiary alcohols right there. Okay. Next, let us see the structure of functional group. Okay, we have general alcohol, phenols and ethers over there. Okay, let us compare the bond lengths and bond angles in between. What I can say, all these three. Okay, generally in this alcohols and ethers, right, the oxygen is sp3 hybridized one. sp3 hybridized in the sense the bond angle should be like 109 degrees, right? Now if you see here, we have ideal bond angles only 108.9, 109, and here it is little bigger because of the groups over there. Okay, no worries. Okay, but let us compare the bond lengths here. Let us compare the bond length. Okay, now what is the actual bond length here between C and O over there? It is 142 picometer, right? Now here how much it is there? It is decreased in the case of phenol, but here it is approximately 141. Okay, these two are like same only, but in the case of phenol only it is being changed. The reason for this one is because of partial delocalization or partial double bond character. Okay, if you take the phenol here, what happens? We have lone pairs, on the oxygen, right? These lone pairs are in conjugation with the double bond of the phenol ring, right? Like benzene ring over there, right? What happens here? Due to delocalization, formation of double bond takes place between carbon and oxygen. Okay, what happens? Negative charge will be formed here and double bond will be formed over here. Okay, due to this particular reason, right, what happens is that the bond length decreases. Okay, here it is 142 picometer and here it is 141 picometer, but in the case of phenol alone it is decreased to 136 picometer. Okay, the reason is partial double bond character. In phenol. Okay, let us see preparation of phenols. Here. Okay, now we have seen preparation of alcohols and the structure of what I can say alcohols and phenols and ethers, right? Now let us see preparation of phenols here. The first preparation method is from haloarenes. Okay, let us take haloarenes here. Let us take chlorobenzene. Okay, chlorobenzene over there. Now the reaction of chlorobenzene takes place with what I can say sodium hydroxide over there at high pressure and high temperature. Okay, high temperature. Okay, approximately 623 Kelvin and 300 atmospheric pressure. Okay, 300 atmospheric pressure. Okay, what happens here is that it's a kind of nucleophilic substitution reaction. Okay, OH group replaces chlorine over there. Okay, now generally these alkyl aryl halides are not ready to undergo nucleophilic substitution reaction because the lone pair participates in the delocalization with the pi bonds of the benzene over there. Okay, that is why they won't readily participate over there, but at extreme conditions only they will undergo nucleophilic substitution reaction where we will get what? Phenols. Okay, this is an example for aromatic nucleophilic substitution reaction. Okay, but we have to remember the conditions at high temperature and high pressure. Okay, let us go with benzene sulfonyl sulfonic acid also. Let us take a benzene right now. Okay, with oleum or H2SO4. Okay, oleum. Okay, it gives benzene sulfonic acid. Okay, this one benzene sulfonic acid. Okay, benzene sulfonic acid, that is SO3H. This is on further reaction with acid. Okay, and some changes in temperature, it gives phenol. It gives what? Phenol. Okay, these are two preparation method. Okay, first one is aromatic nucleophilic substitution reaction. Second one is first what I can say electrophilic substitution reaction followed by a kind of substitution over there. Okay, next let us see from benzene diazonium salt. Okay, benzene diazonium salt. Let us take aniline first. That is NH2. Okay, that is aniline. This aniline on reaction with sodium nitrite and HCl. At 0 to 5 degrees Celsius. Okay, 0 to 5 degrees Celsius, or we can also write it as 273 to 278 Kelvin. Okay, what happens is that diazonium salt formation takes place. Benzene diazonium salt formation takes place. What is this benzene diazonium salt? That is benzene ring N2 plus and Cl minus. Okay, this one on further reaction with further reaction with water. Further reaction with water. What happens here is that like formation of phenol takes place. Formation of phenol takes place by the elimination of N2 and HCl, and by the elimination of what? HCl over there. Okay. Now what we have to prepare? Actually, we have to prepare what? Phenol we have to prepare. Okay. But the same reaction we have seen with the benzene sulfonyl chloride in the previous chapter. What is this one? The Sand-Mayer's reaction. Okay. Here what we will take? Cu2 Cl2 if we take, right, what happens is that formation of chlorobenzene takes place. Formation of chlorobenzene takes place. Okay, this reaction is Sand-Mayer's reaction. This is a normal reaction where we can prepare phenol over there. Okay, let us take from cumin also. Cumin. Okay, isopropyl benzene is known as cumin generally. Let us take cumin first. That is CH3 and CH3. Or else let me take CH3 this side. Okay, CH3 and CH3. This is cumin. This cumin on reaction with O2 gives cumin peroxide over there. What is this? We will get a peroxide right now. Okay, what do we have? COOH and CH3 and CH3. Okay, this on further rearrangement. Okay, this one is on further rearrangement. What happens now? This bond breaking takes place and formation of new bond formation takes place, and this bond comes out over there. Okay, now if you take this particular part alone, okay, this particular part alone, what is this one? CH3 CO CH3 is there, no? That is acetone. Okay, let me take this one. CH3 C double bond O CH3, and remaining part what is there? Benzene ring is there. Okay, benzene ring is there. This benzene ring is forming a new bond with OH group. Okay, OH group, that is nothing but what? Phenol. Okay, now we have seen the preparation methods of what I can say phenols from diazonium salt and cumin also. Okay, now let us see a particular question here. What is this question? Show how the following alcohols prepared by the reaction of suitable Grignard reagent on methanol. Okay, they have given a reagent over there. Okay, generally methanol, if you use what I can say, methanol in the sense that is formaldehyde. Okay, now if you take methanol over here, what we'll get? We'll get what? We know that is CH2OH. We'll get CH2OH. We'll get for sure. Okay, now after getting the CH2OH group, okay, what group is we are using? Okay, like RMGX we are using, right? R-MGX over there. Okay, now whatever group is there in the Grignard reagent, right, that group will come over here. Okay, now what is this group we have? This is nothing but what? R dash over there. Okay, R dash in the sense what is this? Let us take this one, that is CH3 isopropyl one, right? CH3 and what do we have? MgX. If you use this particular reagent over there, we will get what? This particular alcohol over there. Okay, over here also methanol is the common one, right? The alkyl group is this one only. Or like how do we have to prepare that one? Let me take H C double bond O H over here. Now what we are preparing from this one? We are preparing HCOH H. This is the primary alcohol, and we have cyclohexyl, right? Now the reagent which we have to use is that we take this alkyl group, that is cyclohexyl group, and magnesium bromide or halide, whatever it is. Okay. Now whatever the extra group is coming, right, apart from this aldehyde or ketone or like formaldehyde over there, that alkyl group should be coming from what? Grignard reagent. Okay. That part we have to remember when we solve problem from Grignard reagent part. Okay. Next, let us take another one. Okay. Write the structure of the products from the following reactions over there. Okay. Now, what is this reaction? We have already done this particular reaction. What is this reaction? Is acid catalyzed hydration. Okay. It follows Markovnikov rule. Okay. In the Markovnikov rule, negative part of the reagent goes to the carbon with less number of hydrogen. That's what OH comes to the second carbon over here. That is CH3 CH OH single bond CH3. Okay, this is the product. Okay, now if you use this sodium borohydrate, right, this is a mild reducing agent. This cannot reduce C double bond O groups. Okay, this cannot reduce C double bond O group. Okay, this remains constant. But what it can reduce, this can reduce ketones and aldehydes to the respective alcohols over there, right? Now let me take it here. Only this part alone gets reduced to alcohols. Okay, this part alone gets reduced to alcohol, that is OH. And what do we have here? That is CH3 to C double bond O CH3. Ester group remains constant over there, but only one group which is going to be changed here is that ketone group over there. Okay, we have only one aldehyde group. Aldehyde group generally turns into what? Respective primary alcohols with sodium borohydrate, right? Sodium borohydrate can reduce what? Aldehydes here. Okay, let me take it here. That is CH3, CH2, CH3. Okay, this group turns into what? Alcohol. That is CH2OH. CH2OH group. Okay, next. Let us go to the next one. Okay, let us see, like we have seen preparation methods of alcohols and phenols. Let us now see about the physical properties. Okay, generally boiling points of alcohols and phenols increases with increase in the number of carbon. Okay, number of carbons as increases, right? Van der Waals forces also increases. Or you just remember as boiling points are directly proportional to the molecular weight. Okay, as molecular weight of the particular compound increases, boiling point also increases over there. Okay, now let us take the second one here. The OH group in alcohols and phenols involved in intermolecular hydrogen bonding. This is very important. Okay, due to this particular reason, right? Due to this particular reason, alcohols and phenols shows like high boiling points comparatively with ethers over there. Okay, now what is this hydrogen bonding? We know that alcohol, right? What do we have? ROH group is there, right? Now what happens here, since oxygen is like electronegative element, gets a partial negative one, hydrogen gets a partial positive charge over there, right? Now if you take the another group also, what do we have? A partial positive and partial negative, right? Between partial negative and partial positive, there is a attraction formation takes place, right? The attraction between partial positive hydrogen and partial negative, more electronegative which atom is called what? Hydrogen bonding. If it takes place between the molecule, that is intermolecular hydrogen bonding. Within the molecule means intramolecular hydrogen bonding. Okay. Next, boiling points of alcohols and phenols are higher compared to other classes of compounds, namely carbohydrates, ethers, haloalkenes and haloarenes over there. Okay, if you compare the boiling points of alcohols and phenols with hydrocarbons, haloalkenes and haloarenes of same molecular weights, right? This one, alcohols and phenols will have higher boiling point. The reason is they can form hydrogen bonding, as we have already discussed. Okay, and if you take the solubility, right, they are highly soluble in water because they can form hydrogen bonds again. For example, let us take one molecule of alcohol, that is ROH, and let us take one molecule of water. Okay, let us take one molecule of water. Okay, let me take it in different way. Okay, hydrogen, oxygen and hydrogen. Okay, what do we have here is that due to electronegative differences over there, oxygen gets partial negative charge, hydrogen gets a partial positive charge. Here also hydrogen gets a partial positive charge and oxygen gets what? Partial negative charge over there. Due to this particular hydrogen bonding, due to intermolecular hydrogen bonding between alcohols and water, right? They are more soluble in water. We have to remember this particular point. Okay, let us see the chemical reactions. Now generally chemical reactions. Now let us see the chemical properties of alcohols and phenols, right? Now here generally alcohols can act as nucleophile as well as electrophiles over there. In which case they can act as electrophile and in which case they can act as nucleophile. Let us see in this particular slide over here. Okay, now we have two kinds of bonding, right? If you take alcohols, carbon, oxygen and hydrogen. Okay, sometimes the oxygen bond can be broken and carbon bond can also be broken, right? Based on which bonding is going to be broken, we can take alcohols as nucleophiles and what I can say electrophiles over there. Okay, and then let us see the first one over here. Okay, alcohols as nucleophiles. Alcohols as what? Nucleophiles over there. Okay, now alcohols, in the case of alcohols we have oxygen with two lone pair of electrons, right? This lone pair of electrons acts as nucleophile over there. Like this lone pair of electrons for the oxygen like makes it nucleophile. This one can runs to the electron deficient center. Okay, after that it forms a new bond over there. Okay, now in this particular step what is happening is that OH bond is breaking, okay. If OH bond breaking takes place, right, it can act as what? Nucleophile. It can act as what? Nucleophile over there. Now, let us take as electrophile over there, okay. Electrophile, okay. First, what happens? Protonation of alcohols takes place. And in the second step, what is happening is that elimination of water is taking place. Elimination of water is taking place, okay. Now, in this case, what bond is being broken over there? OH bond. Here, sorry, CO bond. Here, OH bond, okay. Whenever, let me take it here, C, O and H, okay. Whenever OH bond breaking takes place, right, that is, here it will act as nucleophile. Whenever CO bond takes place, right, it can act as what? Electrophile. That one we have to remember, okay. Like which case it can act as electrophile and nucleophile, we have to remember. Next, reaction with what I can say, metals over there, okay. In this case, OH cleavage takes place. OH cleavage means what? It can act as what? Nucleophile here. Nucleophile, okay. Generally, whenever metals generally reacts with acid, right, they'll release hydrogen gas. That gas could be tested with what? Burning matchstick gives a pop sound, right? Similarly, here also, if you take alcohols here with the sodium, it gives a salt plus hydrogen gas, okay. This is resembling the properties of acids, right? That's what alcohols also shows certain acidic character, acidic properties, okay. Now, similarly, here also we have tertiary alcohol with aluminum. We have like a particular salt and hydrogen gas has been released. The same thing with like phenol and sodium over there. What is happening here is that releasing of H2 gas is taking place and formation of salt is taking place, right? Which means like alcohols and phenols also show certain acidic character, okay. Now let us see like how it can show the acidic properties over here, okay. Generally, if you take like acidic character of the alcohols, right, it is because of the polar nature of OH bond. Why the polar nature of OH bond? It is because of electronegative difference between oxygen and hydrogen. Okay. For example, let us take one particular example. Okay, let me take ROH. Okay, what happens here is that it releases H plus ions over there, right? H plus ions over there, and the remaining part what will be there, like alkoxide ion over here, alkoxide ion over there. Okay, now this is known as acid. After releasing of the proton, right, it becomes a base. This base is nothing but known as conjugate base. This base is nothing but what? Conjugate base. If the stability of conjugate base increases, the acidic nature of particular acid also increases for any acids, okay. For example, if you take 3 acids, okay, let me take RCH2OH, okay, let's take RCH, ROH, and let me take the tertiary alcohol, okay, R, and OH over there, okay. Now, if you take these 3 over there, as I have already mentioned, okay, the acidic nature of any acid depends on what? Stability of this, its oxide, conjugate base over there, right? If you take these 3 alcohols right now, okay, now in the case of like alkyl group, right, it can act as what? Electron releasing group. This group is what? Electron releasing group, okay. Electron releasing group in the sense what? They can release the electron towards carbon here. Okay. As electron releasing group from primary to tertiary increases over there, electron density on the oxygen also increases. As electron density on the oxygen increases, negative charge increases, it becomes unstable and becomes less acidic over there, okay. That is why if you take the acidic character of alcohols over there, primary is greater than, secondary is greater than tertiary, okay. Primary is greater than, secondary is greater than tertiary over there, okay. Now if you take the acidic characters of phenol over there, phenols are more acidic than that of what? Alcohols over there. It is because of the stability of its conjugate base. Okay. For example, if you take phenol over there, what happens? It forms a phenoxide ion, right? It forms a phenoxide ion by releasing of the proton over there, okay. This phenoxide ion again stabilized with what? The delocalization of the pi bond, okay. Like the negative charge in conjugation with the double bond over there, because of which conjugation takes place, more delocalization takes place, more stability happens in the case of conjugate base of phenol over there, right? As the conjugate base stability increases, what happens? Acidic nature also increases, right? That's what, if you compare the acidic nature of alcohols and phenols will show more acidic character over alcohols over there, okay. Now simply if you take any acid over there, for example, let us take alcohol, ROH, okay. On dissociation, what happens? It forms RO minus plus H plus over there. Let us take rate of forward reaction, okay. What is the rate of forward reaction actually? The rate of forward reaction is nothing but rate constant of forward reaction and concentration of alcohol. if you take rate of backward reaction is nothing but rate constant of backward reaction, and what do we have? Concentration of alkoxide ion and concentration of H plus ions over there. Okay. Now I'll just take these two. What is this one? Like first rate of forward reaction and rate of backward reaction. Okay. Let us take these two. Okay. Now what we'll do here? RF by RB, rate of forward reaction and rate of backward reaction. Okay. Let me take it here. Rate constant of forward reaction and rate constant of backward reaction. Let us take Kf by Kb. Like by taking these two constant, right? Constant by constant, we will get another constant, that is equilibrium constant. We will get, okay. We will get another constant, that is equilibrium constant. This constant, from this one we will get another particular thing. What is this one? We will get Rho minus and H plus by what do we have? ROH, okay, alcohol over there, okay, alcohol, okay. Now, since it is acid, right, this particular constant for the equilibrium is known as acid dissociation constant, If we'll take it as Ka, because it is for acid, right, if Ka value increases, acidic nature also increases over there, okay. Now, because as H plus concentration increases, it becomes what? More acidic in nature, right. Similarly, Ka value also increases, acidic nature also increases. This is what the basic information about like acids and its dissociation over there, right? Now, if you take pKa over there, pKa is nothing but negative logarithm of Ka, over there, okay? Now, as Ka value increases, pKa value decreases. Simply, we can take it as Ka is inversely proportional to pKa, okay? As pKa value increases, Ka value decreases, acidic nature also decreases. Here, what do we have here is that we have pKa over there, right? As pKa value increases, its acidic character also decreases, right? If you take the first one, orthonitrophenol, right? And 10.2, which one is the 10.2 here? We have orthoprazole, and let us take this one, paranitrophenol, okay? 7.1, and the highest one is ethanol, I think, yeah, ethanol here, okay? Now, if you take all these things, right, the lowest pKa value and highest pKa value, right? The one which has lowest pKa value is highly acidic, okay. The one which has like highest pKa value is low acidic one. We'll have like it is low acidic. This is what? Highest acidic one, okay. If you compare the acidic nature of what I can say, alcohols and phenols, right, especially ethanol and phenol over there, phenol is million times more acidic than that of what? Alcohol or ethanol over there. It is because of what I can say, stabilization of conjugate base in the case of what? In the case of phenol over there, right? Let us take esterification over here. Esterification, okay. Esterification is nothing but what? Formation of ester over there, right? We can form esters by taking alcohols and acids, and we can also prepare by taking alcohols or phenols in presence of acidic anhydride, or you can also prepare by taking alcohols or phenols with acid anhydride over here, right? Now, if you take the third one over there, using the pyridine like makes the reaction forward more, because the byproduct which is formed is it is like acidic in nature. Pyridine is basic in nature. Both together, like what happens, removal of product takes place, and what happens is that we can get the pure esters over there. Okay. Next. Okay. Introduction of acetyl group. Okay. Acetyl group CH3CO taken twice O group in alcohols or phenols known as acetylation. Acetylation of salicylic acid produces aspirin. Okay. Now, if we take, for example, what I can say, salicylic acid over here, that is COOH and OH. This is salicylic acid. Now, what has to be done? Acetylation should take place, right? What is this one? CH3CO taken twice, right? That is CH3CO. Okay. Let me take it. Yeah, CO. Okay, taken twice. O gives what? It gives what? Aspirin. What is the formula of aspirin? This particular ester formation takes place with the OH group. Okay, that is nothing but what? Aspirin. Okay, let me take COOH, and here what do we have? O, C double bond O, CH3. This is nothing but what? Aspirin. This is nothing but what? Aspirin. Okay. Next. Reactions involving cleavage of CO bond. Till now we have seen the reaction where OH bond cleavage took place. Now we are seeing the reactions with CO bond cleavage over there. Okay, let us see the reaction with the hydrogen halides over there. Okay, for example, if you take ROH, right, in general, with hydrogen halide, what happens? Elimination of water takes place, and addition of substitution reaction takes place, and formation of alkyl halide takes place, right? The same reactions we have discussed in the case of preparation of alkyl halides also. Now, if we take in presence of ZnCl2 and HCl, right, that becomes a Lucas reagent. It will be used for the distinguishing of primary, secondary, and tertiary alcohols over there. Okay, let us take phosphorus trichloride also. If we take alcohols here, ROH, 3 moles of alcohols reacts with 1 mole of PCl3. Formation of 3 moles of alkyl halide takes place, followed by the formation of phosphoric acid takes place, that is H3PO3. Okay, next. Now let us see dehydration reaction. Okay, dehydration reaction. Generally, dehydration reaction is an elimination reaction. Elimination reaction takes place at high temperature. Okay, if you apply high temperature over there, favors the elimination reaction over substitution reaction generally. Okay, let us take an alcohol here. Let us take an alcohol, that is CH3 CH2OH. Okay, approximately 170 degrees Celsius. What happens is that elimination of water takes place in presence of H2SO4, okay, or some other dehydrating agent, and formation of alkene takes place. Formation of alkene takes place over there. Okay. Now, if we take secondary alcohol, that is CH3OH, and if you take CH3 tertiary alcohol, that is CH3OH. Okay, OH over there. Okay. Now, if you take these secondary and tertiary alcohols, right, the energy which you are supplying, the heat can be reduced over there. Okay, that is why when we take the tendency of dehydration reactions towards all these alcohols over there, right? If you take ease of dehydration reaction by comparing primary, secondary, and tertiary here, tertiary alcohols are more readily undergoes elimination reaction, followed by secondary and followed by primary. We have to remember. Next, let us see the mechanism how dehydration reaction generally takes place. Okay, for example, let us take an alcohol, or else let me take an alcohol, that is CH3 CH2OH. In the first step, what is happening? Formation of protonated alcohol, means protonation is taking place in the first step. Okay, protonation of alcohol is taking place, that is CH3 CH2OH plus. Okay, and in the second step, formation of carbocation takes place. It is an RDS, rate determining step over there. Okay, let me take this one, that is CH3 CH and H, OH and H with a positive charge, right? Now, what happens is that elimination of this water takes place over there. When elimination of this water takes place, a formation of carbocation takes place here. Okay, that is CH3 CH2 plus formation of carbocation takes place. Okay, let us take the third one. Okay, let us take the third one over there, that is CH3 single bond CH2 with a positive charge over there, right? Now, formation of ethene takes place by the elimination of proton. Here the proton gets eliminated over there. And followed by the formation of ethene over there. Okay, this is how this mechanism takes place. Okay, first one protonation, second one is formation of carbocation, which is RDS. You can take it as slowest step, and third one is elimination of proton and formation of alkene over there, formation of alkenes over there. Okay, now let us take oxidation of alcohols over there. Okay, for example, if you take alcohols, right, what do we have? Hydrogen, oxygen, okay, and carbon we may have, right? What do we have here is that, let me take alcohol over there. Okay, now here breaking of this bond takes place, and breaking of this bond also takes place, and formation of new carbon oxygen double bond takes place over there. Okay, now in this case, what is happening? Elimination of hydrogen is taking place, right? Okay, dehydrogenation reaction. Let me write it here. Okay, this reaction can also be taken as dehydrogenation reaction. Dehydrogenation reaction. Dehydrogenation reaction. Dehydrogenation or elimination of hydrogen is also known as what? Oxidation reaction. Okay, oxidation reaction. Oxidation reaction. Oxidation reaction. Okay. Generally, like if you take primary alcohols like CH2OH, CH2OH, on oxidation, okay, on oxidation, they'll turn to the respective aldehydes, CHO, and further oxidation, they'll give what? COOH, okay. To convert this one to this one, right, we required kind of strong, what I can say, oxidizing agent, okay. What are those strong oxidizing agents? We can take KMnO4, potassium permanganate, K2Cr2O7, and Jones reagent, okay. Now, for example, if we take any alcohols over there, for example, let us take CH2OH, right? Let us take chromium trioxide, simple oxidizing agent. It just oxidizes the primary alcohols to the respective aldehyde over there, okay. Now, if you take ketone also, over there, this one reduces, like if you take simple, what I can say, oxidizing agent, right, pyridinium chlorochromate over there, it turns out this one into the respective secondary alcohols over there, okay. Now, generally primary, 1 minute, just made it reverse. Okay, let us take secondary alcohols, that is CHOH turns out into what? The ketones, okay. Now, what I mentioned earlier I mentioned primary alcohols gives the aldehydes, secondary alcohols gives what? Ketones, right? If you use the strong oxidizing agents like KMnO4, potassium dichromate, or Jones reagents over there, the primary alcohols directly turns into what? Acid over here. But if you take the mild oxidizing agents, they'll just turn it into what? Respective oxidized aldehydes are ketones over there. Okay. If you take the tertiary alcohols over here, okay, let us take tertiary alcohols, right? None of these reagents like reacts with tertiary alcohols, but only copper at 573 Kelvin approximately reacts with tertiary alcohols and gives the alkene over there, okay, gives alkene, okay. These are what the oxidizing like reactions of alcohols, okay. Let us go with electrophilic aromatic substitution reactions, okay. Generally, phenol is being an electron releasing group, what I can say, like it can direct the incoming electrophile at orthone para positions, okay. Let us take the phenol here, okay. Let us take different what I can say, electrophilic substitution reactions over there, okay. Let us take nitration, let us take HNO3, okay. Let us take dilute HNO3, okay. During the dilute HNO3, right, only one mono product takes place, only one substitution takes place, that is OH in O2, that is at ortho position substitution, and the second one is para position substitution takes place in O2, okay. But if you take concentrated HNO3, right, what happens here is that trinitrophenol formation takes place. In O2, trinitrophenol formation takes place, okay. If you take just Br2 in non-polar solvent, okay, then like CS2, what happens again? Ortho and para bromophenol formation takes place. Ortho bromophenol and para bromophenol formation takes place. If you take bromine water, right? Br2 in water, what happens is that tribromophenol formation takes place. Br and Br over there, okay. And you can also go with Friedel-Crafts alkylation, acylation, all those reactions takes place with phenol, because like OH group is being a good electron releasing group over there, it can activate the ortho and para centers over here. Okay. If you see the Reimer-Timer reaction over here, phenol on reaction with what I can say chloroform, that is CHCl3 and NaOH, right? It forms a product here, that is OH and CHCl2 formation takes place, okay, Cl2. With NaOH, what happens is that NaOH, nucleophilic substitution reaction takes place. These two Cl groups will be substituted with what? OH groups over here, that is CHOH and OH, okay. This is the general hydroxy group which is unstable, likely to be unstable. What happens? Elimination of water takes place, okay, elimination of water takes place, and what happens? Formation of, this is OH group, okay, OH group, okay, formation of salicylaldehyde takes place, okay, that is OH, and this is CH, okay. This is the formation of salicylaldehyde, nothing but what? Reimer-Timer reaction. Reaction of phenol with zinc dust, okay. Generally zinc could be used for the reduction of phenol over here. If you use the zinc dust over here, what happens here is that it forms benzene followed by the formation of zinc oxide. Zinc undergoes oxidation, phenol undergoes what? Reduction over here, okay. Now this one also can undergo oxidation, which is phenol over there. Phenol can undergo oxidation in presence of sodium dichromate, Na2Cr2O7, okay, forms quinone, okay, quinone, double bond O, double bond O. Next, okay, this is what all about what I can say alcohols and phenol chapter, from preparation to the properties and their structures also we have discussed in this particular chapter, right? Remaining things will be discussed in the next video, right? Thank you for watching.